All right, so here is our lecture for Monday. And like I told you all in class yesterday, this is basically covering evidence that seems to suggest that the Earth is very old. And so as we go through this, we will, but the authors will oftentimes propose an alternative explanation for the data. But some of them they just suggest that we need more research. So first one, and probably the most overwhelming evidence that the Earth is very old, is radiometric dating. And so basically there are a number of different parent-daughter systems that you can use to study radiometric dating. These two are probably some of the most common. You have potassium 40 dating, and you have carbon 14. And both of these, and in all radiometric dating, you have to have some unstable parent material. So in this case, with potassium 40, it's unstable and it deteriorates into argon mostly, although some of it deteriorates into calcium. And then with a half-life of about 1.3 million years, which means after 1.3 million years, half of the original potassium 40 will be degraded into primarily argon, but also somewhat calcium. And the carbon 14 is inherently unstable and deteriorates back into nitrogen, which is actually what it began as before it was bombarded with cosmic rays. So, in order to do radiometric dating, you need an unstable parent material that degrades down into something more stable. And so, at any point, you should be able to measure the ratio of unstable parent to stable daughter and to be able to determine how much time has passed, how many half lives have passed in order to get it to that point. Now, what's interesting is carbon 14 has a half life of about 5,700 years. And so, carbon 14, we talked about this in class, is really useful up to two and a half lives. The full range where carbon 14 can possibly be used goes up to about 60 or 70,000 years. But so if you're trying to date anything older than that, you really can't use carbon 14. By that point, so many half lives have passed that the amount of parent material is minuscule, almost immeasurable. And so that's where you would use, now you would start dating the surrounding rock, and you would use, say, potassium argon dating or some other mechanism. Now, carbon 14 is especially interesting because it doesn't form from carbon, it forms from nitrogen being bombarded by cosmic rays. And so, what that means is you because we have a different source, we have to pay attention to more than just the amount of carbon 12, which is the stable form of carbon, when we're talking about carbon 14 dating. We also have to take into account the relative abundance of nitrogen, and relative abundance is the key word there. But anyways, so for carbon 14, for potassium 40 and other materials, these are inserted into rock as the rock forms. But for potassium 14, what happens is when it forms after nitrogen 14 is bombarded with cosmic rays, some of that carbon 14 is now taken up into carbon dioxide molecules. And because carbon dioxide is used by photosynthetic organisms to generate organic material, some of that carbon 14 gets transferred from carbon dioxide into a sugar or some other organic molecule synthesized by a producer. And then as those producers are consumed by consumers, that carbon 14 transfers over into consumers. And then once at the point at which that consumer dies, that carbon is no longer being converted from organic material back into carbon dioxide. And at that point, basically, your clock starts. And then you can determine the relative abundance of carbon 14 to nitrogen 14 at the time at which a living organism dies. And then if you have an organism that died some time ago, you can compare your ratio of carbon 14 to nitrogen 14 to what it typically is right when an organism dies. And so you can use that to determine the date. Now, we know from doing these radiometric dating or these radiometric dating mechanisms that we oftentimes date biological material to tens of thousands of years, which is longer than what the Bible seems to suggest the earth has actually existed. And so we have somewhat of an issue here in trying to figure out what's actually going on. And then when you talk about potassium argon dating or some other mechanism where you're dating the rock, we regularly have rocks that will date to 540 million years. That'll date as Cambrian rocks. And so we have some issues here, and overwhelming evidence that the Earth is very old. Now, carbon 14 really shouldn't be used to date anything older than 50 or 60,000 years or so. Sometimes it is, and at that point, we really need to draw those pieces of information into question. But anyways, yeah. So both of these mechanisms illustrating that the Earth is very old. But now there has to be some alternative explanation for this, and what we tend to reference are the assumptions, of these dating mechanisms. So let's start with carbon 14. First assumption is that the decay rate is constant. As far as we can tell, this seems to be very well supported by the data. Now, the next assumption is that the amount of carbon dioxide in the atmosphere has always been constant. And if you have more carbon dioxide in the atmosphere, you have less relative nitrogen that can be converted into carbon 14. And so if at any point in the Earth's history you had more carbon dioxide than you do now, which there are evidence to suggest that there were points in Earth's history in which the carbon dioxide levels were higher than they are now, then you would have less relative nitrogen, therefore less material to be converted into carbon 14. You would have relatively less carbon 14 in the past than you do now, would dilute that carbon 14 and would force things to date older than what they really are. Another one is the amount of cosmic rays have always been constant. Now this, we have several reasons to suggest that this might not be the case. One is more of a theoretical one, and we see very long ages of humans prior to the flood, which seems to indicate that there is very little mutation going on from radiation from the sun. And so it seems to be that the amount of cosmic rays increases after the flood compared to what it was beforehand. And then also we can actually see that this rate of carbon 14 is going to vary a great deal. The conversion of nitrogen 14 into carbon 14 is going to vary a great deal by the amount of moisture that's in the Earth's atmosphere. And so there have been times in Earth's history where it seems that there was significantly more moisture in the environment because you had almost global tropical environments. And so in that case, you would have a great deal more moisture in the atmosphere, which would lower the amount of cosmic rays. The fourth and final assumption is that plants take in carbon unselectively. That is, that plants take in carbon dioxide with carbon 14 just as readily as they do carbon dioxide with carbon 12. This is true for some plants, for many plants, but some plants do actually selectively prefer carbon 12. And so What this means is that we have to take this into account with some of our fossil plants. Now, what's interesting is we have evidence to suggest that these last three assumptions might not be true, which leads us to question carbon 14 dating. Another thing that leads us to question carbon 14 dating is when you date carbon from oil deposits and coal deposits, you get an actual date. From there's still carbon 14 left around, enough to actually date them based on the amount of nitrogen 14 that's in that. But these deposits are supposed to be very, very old, many of them Devonian and even older, and by that point there should be absolutely no carbon 14, and yet they are still dating. All right, now for other radiometric dating parent and daughter systems, we assume that the decay rate is constant. The evidence seems to suggest that that's fine. The rock remained a closed system. That is, that after the rock formed, no parent or daughter material could enter and no parent or daughter material could leave. We do have a great deal of evidence to suggest that that is not the case, that rocks are not closed systems. Material enters in and leaves. And then the last one, that the radiometric clock was set to 0. That is, at the time in which the rock formed, all daughter material was absent, was pushed out before the rock formed. Again, we have evidence to suggest that this is not the case, leading us to question whether or not these are actually providing accurate dates. Now, there's no doubt that these are providing good relative dates, that if something dates to be 540 million years old and another rock dates to be 400 million years old, that 540 million year old rock is older than the 400 million year rock. But because the radiometric clock probably was not set to 0 in many cases, these are not representing actual ages, but instead are representing relative ages. So, some other dating mechanisms. Oh, and then the textbook does talk a little bit about that it's interesting that most deposits that are early Cenozoic, or many deposits that are early Cenozoic, give you carbon 14 dates somewhere around 60 to 70,000 years, which the authors of the textbook suggest that that's probably what it should date immediately following the flood, and then that the rate of decay, not the rate of decay change, but the actual relative ages you would get because of the changes in the amount of carbon 14 produced in the atmosphere, because lower levels of carbon dioxide or lower levels of moisture, that's going to slow down. And so something immediately following the flood should date to about 60 to 70,000 years. And then as you get closer to modern time, you should get to something that is more closely related, or more closely related to what the actual time is. Sorry. Now, two other dating methods. Now, these are not independent of radiometric dating. In fact, they are calibrated on radiometric dating, but they are evidences of long periods of time. So you've got magnetic stratigraphy, where you can see the reversal of the Earth's magnetic field. Here you have all of your dark bands are instances of regular or normal polarity, where the North Pole is the North Pole and the South Pole is the South Pole. Any white areas is where you have reversed polarity, where the South Pole is now the North Pole and the North Pole is the South Pole. And so while this date is calibrated on radiometric dating, it does seem to suggest a long period of time in order to reverse that polarity. Now, some researchers have attempted to explain how you could rapidly reverse this. David Humphreys is one of them, how you could rapidly reverse a magnetic field. And so there are some pieces of evidence to suggest that this could happen in a period of days, where you could reverse the magnetic field. The other one is amino acid racemization. So, in living organisms, the amino acids are entirely the L form. And so, amino acids have two isomers that are mirror images of one another, the L isomer and the D isomer. And in living organisms, all of the amino acids have the L isomer. But at the point at which an organism dies, it starts to change to a racemic mixture to where you have 50% L form and 50% D form. Now, the rate of racemization is not constant. The rate of racemization changes based on how much of that material is left. And so the rate at which this racemization is happening, and so the faster it's happening seems to suggest a younger age, and then the slower it's happening seems to suggest an older age. The closer you get to that 50-50 mixture, the slower the conversion actually happens from L form to D form. And so this suggests, again, this is one that is calibrated with radiometric dating, but it does seem to suggest an older Earth to give enough time for this to actually happen. Although, if we actually keep this rate constant and it doesn't change as you get closer to that 50-50 mixture, then this could actually happen in a period of a few thousand years, as opposed to happening over hundreds of thousands or even millions of years. All right. So there are many cyclic sedimentary features that seem to require a significant amount of time. One are tidal cycles, where you have evidence of high tides and you have evidence of low tides. And so these tidal cycles leave records in the sand. And so it seems to suggest not necessarily a yearly event, but they seem to still indicate something that would take a decent amount of time. And so we've got evidences of a certain number of high tides and low tides, and this might be challenging to account for in a single year of a global flood. Now, to account for it in hundreds or a few thousand years is not an issue, but to account for all of the Paleozoic and Mesozoic being laid down in a single year is challenging because of these evidences of a certain number of high tides and low tides. Now, you have this thing that's called a varve, where we tend to have one lamination formed per year, and there are a number of examples of these. And so a number of these deposits will contain, hundreds of thousands of these varves. And again, if you interpret them as a single year, these forming each layer, then it gives overwhelming evidence for really, really long ages. However, what's interesting is in the Green River Formation, we have, when we've talked about this before, mass burial of millions of fishes. We've got mass burial of turtles. We have our oldest fossil bats. We've got just a rich fossil bed, and they will be buried with sometimes hundreds or even thousands or tens of thousands of varves, suggesting that these are not yearly cycles, because this is suggesting mass burial, and you've got what might be tens of thousands of varves in something that had to be buried rapidly enough to fossilize it. Glacial ice cores, where again we've got this idea of a single layer formed every year, is suggesting that some of these glaciers are hundreds of thousands or even millions of years old. Although once you get really deep into a rock, compression tends to erase these lamini, I think is, but these layers, And so then we would use things like volcanic eruptions and the presence of ash in there to try to date these. Again, suggesting long ages, but alternative explanation, we find a section in Greenland that was abandoned during World War II. And in 46 years of time, you formed 90 meters of ice over that plain that was abandoned, containing hundreds of layers of ice. And so in 46 years, you had hundreds of layers form. And so Laminy, again, suggesting that it's not really annual. And then as far as the volcanic ash is concerned, it's very difficult to match a specific eruption to that ash. Most eruptions elicit ash that is very similar. All right. So, what other evidence are there? One is laccoliths, where you have a massive amount of molten magma intrude through the sediment and then cool to form a massive igneous rock. Now, as you can imagine, here we've got a laccolith here, beginning of Cenozoic deposits. It would take a really long amount of time to cool this amount of rock. And so again, this is suggesting that the Earth is very old. Now there are some creation geologists, Andrew Snelling and John Woodmorap, that have worked on studying the cooling of granitic magmas and said that you could dissipate that much heat within the time with a young Earth. Especially if you've got waters draining off of the Earth at that time to help cool these rocks, although we need more evidence in that area. Glacial movement it seems to require a long amount of time for these glaciers during the Pleistocene Ice Age to advance and retreat, many times leaving evidence in the underlying rock of those advances and retreats. And this is one where we really don't have a good explanation for this just yet. The amount of sediment that we know that erosion can happen very quickly when you have massive amounts of water, as can transporting a lot of material. But the question is, where did all of this material come from in order to lay down the entire fossil record in a year? So if you're going to bury the amount of material that we do during the Paleozoic and Mesozoic in a single year, you're going to need an enormous amount of sediment. And so a possible explanation for this is that the amount of sand may have been formed during the Precambrian, or that the sand was actually an extensive component of pre-flood soil. Plate tectonics, we talked about this actually a pretty good deal in class. We've got overwhelming evidence. Here's the Mid-Atlantic Ridge, and I showed you following the contours of the coastline. When you take the entire continent, you've got fossils that overlap in these areas. You have these continents that fit very nicely together. We have pretty overwhelming evidence of plate tectonics, and again, because of heat issues, we suggest that this would take. It suggests that this would take a pretty decent amount of time, and so this is something that's pretty challenging. We have to figure out how you can have that happen in a short amount of time, and where does all that heat that gets generated actually go. And so the last couple of evidences are biological. One is we have evidence of an enormous number of reefs. And so here you can see coral reefs and just the number of coral reefs, where we find them in the fossil record. And then here you can see the number of reefs, total number. This is reefs thicker than 100 meters. And so we've got a number of those reefs throughout the geological column. And so reefs take a while to build. And so these obviously could not be built during, if you're going to have a year of time going all the way from here to here, your Devonian is lasting maybe a month of time. And that's not going to be enough time to build 50 reefs that are all 100 meters thick. So the only way to really address this is that either these aren't really reefs and have been interpreted as incorrectly. There is quite a bit of evidence of that many things have been interpreted as reefs and then have been reinterpreted as something else. Or that these reefs were built prior to the flood and were moved to where they were buried. During the tsunami in 2004, a number of reefs were ripped out and were taken and deposited somewhere else. So there is evidence that you could move reefs quite a bit, actually. So then there are bioturbation where you've got evidence of animals digging through the materials, but this one's stromatolites. So stromatolites, we have a number of areas throughout the fossil record where you've got these structures built by cyanobacteria pulling material out of the ocean, and it takes time to build these, as you can probably imagine. And so having a number of these in early Paleozoic deposits suggests that those could not be built in months, at most probably weeks, during that time of the global flood. So would either have had to been built before the flood and then deposited somewhere else in their current state, or it would have had to take more time than what we really think. And so, again, there's some challenges. Our presentation for Wednesday, we're going to talk about evidences that suggest that the Earth is very young.